Welcome back, everyone, to another deep dive. You know we love to untangle complex topics, and today's no different. We're diving headfirst into a world where shapes meet algebra.
A world of mirrors.
Exactly. It's a paper called...
Edge subdivisions and the L2-homology of right-angled Coxeter groups.
Right. And it really challenges some long-held beliefs in topology.
It really does.
Send over the paper itself.
I did.
By Grigori Avramidi, Boris Okun, and Kevin Schreve.
Yeah.
Published just this week, November 13, 2024.
Hot off the press.
Piping hot. So, are you ready to unpack it?
I'm ready. Let's get into it.
Okay. Before we get lost in the weeds, could you just give us a quick overview of, the main idea? What are these authors trying to do?
Well, they're exploring this thing called L2 homology and how it changes when we modify these things called Davis complexes. And they do this through edge subdivision. And by doing this, they're seeing how these changes support or contradict conjectures in topology, specifically the Singer conjecture and the torsion concentration conjecture.
Oh, okay, I see. Now, for our listeners who might not be totally up on this stuff, can we back up a bit? Can you remind us what right-angled Coxeter groups are? Why are they important here? RACGs.
Right, RACGs. So basically, they're groups generated by reflections. The only relations are that each generator squares to the identity and certain pairs of generators commute.
So it's like a bunch of mirrors, but some of those mirrors play nice with each other.
That's a great way to put it. And the really cool thing is the structure of these groups is captured by something called a flag complex.
Ah, flag complexes. They always sound so mysterious. Can you break it down for us?
Sure. Imagine a simplicial complex. Now, in this complex, every complete subgraph forms a simplex. That's a flag complex. It's like a blueprint for the RACG. So each vertex in the flag complex represents a generator in the group. And if you have an edge between two vertices, that means their generators commute.
So the flag complex tells us which mirrors can reflect without messing things up, right?
Exactly.
Now, to actually visualize these RACGs, we use these Davis complexes. Can you explain those a bit more?
Yeah. So a Davis complex is a space associated with an RACG. Think of it like a mirror world. It's built from copies of a fundamental domain, which is like a basic building block that represents the group's action.
And each mirror, each reflection is like creating a copy of that building block.
Exactly. They tile together based on the relations in the RACG. And you get these amazingly complex patterns, especially in higher dimensions.
You mentioned they have a natural cubical structure.
Yeah, so each fundamental domain is like a cube. These cubes are glued together along their faces, all based on the rules from the RACG.
So we're building with higher dimensional Legos. And the flag complex is our instruction booklet.
Precisely.
All right, so we've got RACGs, flag complexes, Davis complexes. Now let's jump into the deep end. L2 homology. Can you try to give us an intuitive sense of what it is and why it matters here?
Okay, so imagine you have a loop in some space. L2 homology helps us see if we can fill that loop in, but here's the catch. We're working with infinite dimensional spaces, so we need tools from functional analysis, Hilbert spaces, things like that.
So instead of shapes, we're thinking about functions and infinite dimensions.
Exactly. And L2 homology helps us understand the size of these infinite spaces. It connects to the geometry of the original complex.
Now, how does the Singer conjecture fit into this? You mentioned it earlier.
Right. It's this major unsolved problem in topology. It predicts that the L2 homology of certain spaces, including our Davis complexes, will vanish outside the middle dimension.
Vanish? Like equals zero. What does that mean?
It means there are no interesting loops or holes in those dimensions. Like the space is flat, but in a very specific L2 homology sense.
Interesting. So the authors want to see if edge subdivisions and Davis complexes support or challenge the Singer conjecture.
Exactly. And this brings us to the idea of edge subdivision itself.
Right. Can you explain what an edge subdivision is? Why would we want to do that to a Davis complex?
Sure. It's a really simple operation. You take an edge and split it into two by adding a new vertex in the middle.
So we're adding more Legos to our structure. Doesn't that make it more complicated?
It does. But that's what's fascinating. The authors show even this tiny change can have a huge impact on the L2 homology.
So subdividing edges changes not just the shape of the Davis complex, but also its L2 homology. And that could affect the Singer conjecture.
Precisely. To analyze these changes, they use a powerful tool from algebraic topology, Mayer-Vietoris sequences.
Were those like a mathematical microscope?
You could say that.
Yeah.
They help us break down the L2 homology into smaller, more manageable pieces. We can really see the fine details of how the edge subdivision is affecting things.
Okay, I'm following so far. But then they bring in this whole other area of math. Skew fields.
Right, and this is where things get really interesting.
Can you give us a quick intro to skew fields? They sound a bit intimidating.
Imagine a field like the real numbers, but multiplication isn't necessarily commutative. A times B doesn't always equal B times A. That's a skew field.
So the usual rules of arithmetic get a bit wonky.
In a way, yes, but there's a specific type called a Linnell skew field. It gives us a universal way to compute these things called L2-Betty numbers.
L2-Betty numbers. How do they relate to all this?
They're like measurements that come out of L2 homology. They quantify the size of those infinite spaces we were talking about.
Okay, so Linnell's skew fields help us calculate these L2-Betty numbers, which tell us about the L2 homology, which relates to the Singer conjecture. It's all connected.
Exactly. And because of this universality of Linnell's skew fields, the authors can do something really clever. Instead of adding vertices, they can essentially remove edges while still controlling the L2 homology.
Wait, remove edges instead of adding them? How does that work?
It simplifies things. They can relate the original Davis complex to a simpler one. This leads to a key result. Theorem 3.3.
Theorem 3.3. That sounds important. What does it say?
It states that if the original complex has vanishing L2 homology in a specific dimension, so does the simpler complex you get by removing an edge under certain conditions.
So it's a shortcut. We can learn about the complex by studying a simplified version.
Exactly. And this paves the way for relative barycentric subdivisions.
More new terminology. What are those?
Imagine you have a complex with a subcomplex inside. You subdivide the whole complex, but you keep that subcomplex fixed. That's a relative barycentric subdivision.
It's like a more targeted subdivision.
Precisely. And crucially, you can build these from a series of edge subdivisions. This is key to proving Theorem 4.16.
Theorem 4.16. It seems like a big deal. What's it about?
It confirms the Singer conjecture for a specific family of spaces. It says that for Davis complexes built from these relative barycentric subdivisions, the L2 homology vanishes outside the middle dimension.
So they found a bunch of spaces where the Singer conjecture is true. That's big.
It is, and the proof is really elegant. It combines edge subdivisions, Mayer-Viator sequences, skew fields, everything we've talked about.
Wow, it sounds like a complex mathematical tapestry.
It is, but there's more. The paper also explores torsion growth.
Okay, another new term. What's torsion growth?
It measures how the torsion part of homology groups grows as you look at smaller and smaller subgroups of the RACG.
Torsion part. Remind me what that is.
It's about elements with finite order. Think of a loop. If you go around it enough times, you get back to the start. Torsion growth tracks how many of these finite loops you find in different subgroups.
So it's like measuring the loopiness from a different angle.
Exactly. There's this conjecture called the torsion concentration conjecture. It predicts how torsion growth should behave in certain spaces. Similar to the Singer conjecture, but about torsion.
Did the authors prove this one too?
That's where things get really interesting. They actually found counterexamples to the torsion concentration conjecture.
Wait, they disproved it?
Well, not completely, but they showed it doesn't always hold. They found examples where torsion growth behaves unexpectedly.
Wow. So just by looking at edge subdivisions, they discovered new things about both L2 homology and torsion growth.
Exactly. And those counterexamples are really valuable. They force us to rethink our assumptions and dig deeper.
It's like they opened a Pandora's box of new questions.
Precisely. And those questions are what keep math exciting.
Welcome back. We're dipping deep into this paper, and wow, those counterexamples to the torsion concentration conjecture are still rattling around in my brain.
It's pretty wild, right? Shows you there's always more to learn, even in areas you think are well trodden.
For sure. Before we wander too far, could you walk us through how they built those counterexamples? It sounds pretty intricate.
It is, and it all starts with a very particular flag complex. The authors call it OL.
OL, okay. What makes this flag complex so special?
Well, it's three-dimensional, and it's got this unusual quirk with its L2 homology. When you use rational coefficients, it vanishes outside the middle dimension like we'd expect. But when you use coefficients from a finite field, it doesn't vanish.
Ah, so that's where those Linnell skew fields come in. Different coefficients, different L2 homology groups. And I guess that leads to different torsion growth behavior too.
Exactly. The authors use this subtle difference in L2 homology to build their counterexamples. They start with the Davis complex for the AOL flag complex, and then they apply a bunch of relative barycentric subdivisions.
Okay, so by picking those subdivisions carefully, they can tweak the torsion growth to break the torsion concentration conjecture.
Precisely. And this is where those universal coefficient theorems we talked about earlier become super important.
Right, those were the tools that helped us translate between different types of homology.
Exactly. They link homology with integer coefficients to homology with coefficients in other structures, like those finite fields we mentioned.
So using those theorems, the authors showed that if the L2 homology vanishes outside the middle dimension, then the torsion growth should be concentrated in a specific way.
Precisely. But their counterexamples prove that this concentration doesn't always happen, even when the L2 homology vanishes as expected.
So the LL complex is like this hidden bomb. It looks normal on the surface, but it packs this unexpected torsion growth.
I love that analogy. It really highlights how important it is to look at different coefficient systems. Rational coefficients don't tell the whole story.
This is all fascinating stuff, but I'll admit I'm still grappling with the big picture implications of these counterexamples. What do they mean for our understanding of topology?
Show that the connection between L2 homology and torsion growth is much more complicated than we thought. The torsion concentration conjecture painted a nice, neat picture, but these counterexamples shattered that. There are hidden depths we need to explore.
It's like we were following a straight road and then bam, we hit a fork, and now we need to figure out which path to take.
Exactly. And that's what makes these counterexamples so exciting. They challenge us to rethink our assumptions and explore new avenues.
Instead of roadblocks, they're more like signposts, pointing us in new directions.
I like that. And speaking of new directions, you mentioned minimally branching complexes earlier. How do those fit in?
Right. Refresh my memory. What makes a complex minimally branching?
It's about how much the complex branches out. So in a minimally branching flag complex, every simplex of dimension n2 is contained in, at most, 3 simplices of dimension n1. It's like the branching is very tightly controlled.
Okay, so a very specific type of structure. What did the authors find out about their L2 homology?
They proved this amazing theorem, Theorem 6.1. It says that for minimally branching complexes, the L2 homology in the top dimension vanishes unless the complex has a very particular structure, something called an n-fold join of 3 points.
An n-fold join of 3 points. Remind me what that is.
It's like a souped-up triangle. You start with 3 points and make a triangle, then you connect those triangles to make tetrahedra, then you connect those to make 5 simplices, and so on, going up in dimensions.
Ah, okay, I'm visualizing it. So this theorem is saying that most minimally branching complexes have vanishing L2 homology at the top, unless they have this very specific triangle-based structure.
Exactly. And this has some interesting consequences. It suggests that the branching pattern of a complex really shapes its homological properties.
So we've got combinatorics, geometry, topology, all coming together to give us a fuller picture of these complex spaces.
Exactly. It's this interconnectedness that makes math so beautiful and thought-provoking.
We've covered so much ground already in this deep dive. Coxeter groups, Davis complexes, L2 homology, even those crazy skew fields.
It's been quite a journey, and we've only just scratched the surface of this paper. There's so much more to discover.
Well, on that note, let's take a moment to gather our thoughts, and then we'll come back for the final leg of our deep dive.
Sounds good to me. There's a lot more to unpack and discuss.
And we're back. Our deep dive into edge subdivisions and the L2 homology of right-angled Coxeter groups has taken us through some wild terrain. Coxeter groups, Davis complexes, L2 homology, even those skew fields, right?
It's been a whirlwind tour, for sure, and we've unearthed some surprising results along the way, especially those counterexamples to the torsion concentration conjecture. Those were big.
Yeah, those really shook things up. It's wild how something as seemingly simple as edge subdivision can have such a huge impact.
It just shows you how interconnected math is. A tiny change in one area can cascade through the whole system.
Okay, so now that we've got the nuts and bolts of this research down, I'm curious about the bigger picture. What makes these findings so important to the world of topology?
Well, for one thing, it's a big step forward for the Singer conjecture. By proving it for this new family of spaces, those Davis complexes from relative barycentric subdivisions, the authors have given us more tools to attack this problem.
So it's not just about confirming the conjecture in these specific cases, but about building up a whole new set of techniques that could help us prove it more broadly.
Exactly. And those counterexamples to the torsion concentration conjecture, they're just as important, even though they might seem like setbacks at first glance.
Yeah, I was thinking of more like roadblocks. We were cruising along, feeling pretty confident, and then suddenly, detour.
But detours can be a good thing. They force us to reevaluate and look for new paths. These counterexamples tell us that the connection between L2 homology and torsion growth is way more complicated than we thought.
So instead of seeing them as failures, We should see them as opportunities to learn more.
Exactly. They show us where our current models break down and point us toward new things to explore.
Makes sense. So looking ahead, what are some of the big questions that this paper opens up for future research?
Well, one clear direction is to see if we can push these techniques further. Can we build on these relative barycentric subdivisions and edge removals to prove the Singer conjecture for even more types of spaces?
It's like they've handed us a new set of tools, and now we need to figure out how to build something even more impressive with them.
Precisely. Another exciting avenue is to really delve into those counterexamples to the torsion concentration conjecture. What's going on under the hood there? Is there a deeper pattern we're missing?
It's like those counterexamples are a treasure map leading us into uncharted mathematical territory.
I like that. Who knows what we might find along the way? Maybe a more refined conjecture that accounts for those counterexamples, or a new set of invariants that capture the subtle interplay between L2 homology and torsion growth.
It's exciting to imagine the ripple effects this research might have on other areas of math, or even beyond math.
Absolutely. L2 homology and torsion growth touch on so many fields: geometric group theory, representation theory, even theoretical physics. There's no telling how these findings might shape future research.
It's like dropping a pebble in a pond and watching the ripples spread out, touching things in ways you never expected.
Beautiful analogy, and I have no doubt the impact of this paper will be felt for years to come.
This deep dive has been a wild ride. We've climbed mathematical mountains, navigated twisty paths, and caught glimpses of vast, unexplored territories.
And it all goes to show the power of human curiosity and our drive to understand the mysteries of the math universe.
It's a journey that never really ends, always leading to new challenges and deeper understanding. Thanks for joining us on this exciting adventure. All right, let's jump into a world where shapes and symmetry collide with something called L2 homology. We're talking right-angled Coxeter groups.
Yeah.
You can kind of think of them like mathematical kaleidoscopes. They make these really complex patterns.
Yeah, it's wild how these groups, even though they're abstract, they connect to how we understand the shape of space itself. And you even find them popping up in things like how certain matrices are arranged. It's really fascinating.
Our source for this deep dive is Edge Subdivisions and the L2 Homology of Right-Angled Coxeter Groups. It's by Avramidi, Okun, and Schreve, and it's dated November 13, 2024. And, I'm really intrigued by how these kaleidoscope patterns, as we're calling them, can actually change the L2 homology, which is, as I understand it, like trying to measure these holes in a space that we can't even really picture.
Yeah, that's a good way to think about it. It's like if you rearrange the furniture in the house, does it change how many rooms there are?
Yeah.
But imagine doing that in a space you can't even visualize.
Okay, so we've got this conjecture about these holes, and we're trying to see how tweaking these right-angled Coxeter groups affects things. What are the specific examples that they use in the paper?
They focus on barycentric subdivisions of triangulations of spheres. Imagine taking a triangle and then dividing it into 6 smaller triangles. Like you connect each vertex to the midpoint of the opposite side.
Right.
You're essentially creating this finer mesh, like zooming in on a shape in a very specific way.
So they're basically making the kaleidoscope even more intricate.
Yeah.
And then seeing how that impacts the L2 homology. What are some of their key findings?
Well, the paper really dives into how hard it is to actually verify the Singer conjecture for spaces that are constructed from these right-angled Coxeter groups. And by using these specific examples of barycentric subdivisions, they can observe how even just these tiny little changes in the triangulation can cause the L2 homology to vanish in certain dimensions.
Vanishing L2 homology, that's a pretty wild outcome. How do they even go about studying something like that? It sounds incredibly complex.
Well, they use a really clever method using something called skew fields. It's a way to study L2 Betty numbers, which essentially help us quantify these abstract holes we keep talking about. And they specifically zero in on what are known as Linnell skew fields. They have these unique properties, and they really simplify the calculations involved. It's like they have this special tool that allows them to see these holes more clearly.
So these Linnell skew fields help them see the L2 Betty numbers, which are telling us about these holes. And they're looking at how those numbers change when they do these subdivisions. So what's the connection then between these skew fields and the actual homology itself?
Well, the Linnell skew fields let them connect the L2 Betty numbers, which are normally calculated using analytical methods, to Betty numbers that they can calculate using these skew fields. It's like they're building a bridge between two different mathematical worlds.
I see. So they're connecting these two different ways of looking at Betty numbers. How does that actually help them in their research?
Well, this connection allows them to create these inequalities between L2 Betty numbers of different spaces. And then these inequalities, in turn, lead to the vanishing results we've talked about, where certain L2 homology groups become zero after you do the subdivisions.
We've been using this term right-angled Coxeter group quite a bit. I think it's time to break that down a bit. I need a visual, personally, to really wrap my head around this.
Sure. Picture this. You've got mirrors, right? And they're arranged in these specific patterns. Each reflection in a mirror, that creates a new element of the group. That's the essence of a right-angled Coxeter group. You start with these generators, which are the basic reflections, and then you combine them to create these more complex elements.
So the way the mirrors are arranged is kind of like the rules of the group, right?
Exactly.
What do they use to actually visualize these groups and their structure?
Well, for each of these groups, there's a geometric construction associated with it called the Davis complex. And it's built from these copies of a simpler shape that's linked to the group. You can think of it like building a castle out of Lego blocks. Each Lego block is the same, but together they create this complex structure.
That's a really helpful analogy. So within this Davis complex, are there any smaller structures or elements that they focus on?
Yes, there are these special subcomplexes called flag subcomplexes.
Okay.
Think of them as like if you focus on a single turret in that Lego castle instead of looking at the entire structure as a whole, they capture these smaller patterns within the larger group. And the authors use these flag subcomplexes along with something called Mayer-Vietoris arguments to break down the Davis complex and really study its homology.
Okay, let's break that down a bit further. What are these Mayer-Vietoris arguments? And how do they actually help with studying the homology?
Imagine you're trying to understand this really complicated maze. A Mayer-Vietoris argument is like strategically breaking that maze down into smaller, more manageable sections.
Okay.
By looking at each section individually and seeing how they connect to each other, you can eventually piece together the structure of the entire maze.
So they're using these arguments to analyze the L2 homology of the Davis complex, like piece by piece.
Exactly. They break it down into these smaller flag subcomplexes and study how they connect. And this, combined with the properties of the skew fields, helps them understand how changing the fundamental structure of these groups impacts their L2 homology.
I see. So they're taking this complex problem and sort of using these techniques to break it down into smaller, more manageable pieces. Now, going back to subdivisions, why are they so important in this context? Why are they focusing on them?
Well, subdividing the Davis complex, like we talked about with the barycentric subdivisions, is like adding more mirrors to our kaleidoscope analogy.
Okay.
You get a more intricate pattern. It's basically refining the complex's structure.
And they're looking at how these subdivisions then change the L2 homology, right? What kind of subdivisions do they use? Are there different types?
They focus on a particular type called relative barycentric subdivision. Think of it as deliberately placing those extra mirrors in a controlled manner. They want to isolate specific effects.
Right.
It allows them to make very targeted changes to the complex.
Oh, so they're not just randomly adding mirrors, they're being very strategic about it. What do they find when they use these relative barycentric subdivisions?
The key results are actually presented in theorems 4.16 and 4.17 of the paper. These theorems show that subdividing specific edges, very particular ones, can actually make certain L2 homology groups vanish.
That's fascinating. So they can pinpoint which parts of the kaleidoscope need to be tweaked to make these certain holes disappear. What does this tell us then about the Singer conjecture itself?
Well, these results give us new insight into whether the Singer conjecture actually holds true for certain spaces. For example, they prove that it does hold for spaces constructed from these barycentric subdivisions of triangulations of even-dimensional spheres. It's a big step forward in understanding this conjecture and what it means for both topology and geometry.
This is all really interesting, but I have to admit, my brain's starting to feel a bit overloaded. Can we do a quick recap of what we've covered so far?
Sure. We started by exploring these right-angled Coxeter groups, how they're structured, and how they relate to the Singer conjecture. We talked about the tools mathematicians use, like Linnell skew fields and those Mayer-Vietoris arguments, to study these groups.
Right, and then how subdividing the Davis complex, specifically using relative barycentric subdivision, allows the authors to really analyze the L2 homology of these spaces and then prove the Singer conjecture for those specific cases.
Yeah, exactly. We've seen how even these small changes to these somewhat abstract mathematical objects can really have a big impact on their properties and how we understand these larger mathematical conjectures.
This has been an incredible deep dive so far. We've gone pretty deep into this world of right-angled Coxeter groups, their L2 homology, and the implications for the Singer conjecture. But we're not done yet. There's still more to unpack in this paper. Before we jump into the next part, I'm curious about a specific section that caught my eye. Minimally branching complexes. Could you give us a quick explanation of what those are?
Sure. A minimally branching complex is a specific type of flag complex where every n2-dimensional simplex is contained in, at most, 3 n1-dimensional simplices. Picture a network of lines, and at no point do more than 3 lines meet. That's essentially what a minimally branching complex is.
Okay, interesting visual. What makes these complexes relevant to the paper, though?
The authors use them to show another cool application of their results on edge subdivisions. Theorem 6.1 in the paper says that for a minimally branching complex, the L2 homology vanishes in the top dimension. Unless that complex is a very specific type, it's called an n-fold join of 3 points. It's like another piece of the puzzle showing how these abstract mathematical concepts actually have some concrete consequences.
It really shows how interconnected different areas of math can be. I'm really excited to see what other connections they uncover as we continue. We'll be back in part 2 to delve even deeper into these fascinating concepts.
Welcome back to our deep dive. Last time we were talking about these minimally branching complexes and how they relate to that vanishing L2 homology. The paper really goes into a lot of mathematical detail to explore these concepts, especially when it comes to these things called skew fields. We touched on them a little bit before, but I think it's worth digging a little deeper.
Yeah, I remember you describing them as like these special algebraic structures that are super important for studying L2 homology. But I'll be honest, I'm still a bit fuzzy on what they actually are.
Okay, so think about skew fields, sometimes called division rings. They're kind of similar to fields in algebra. You have your usual operations, addition, subtraction, multiplication, division, all that good stuff. But there's one key difference.
Okay, what's that?
Multiplication isn't always commutative.
So A times B doesn't always equal B times A. What kind of impact does that have?
That's what makes them skew. It seems like a small thing, but it actually has huge implications for how they behave. They're quite different from the fields that we're usually used to working with.
Right. Okay, I can see how that would make things interesting.
Yeah.
What about these Linnell skew fields specifically? What makes them, the choice for this paper?
Linnell skew fields, they're a specific type of skew field, and they work really, really well with group rings. They have this really cool property called universality, which makes them super powerful for studying L2 homology.
Universality, that sounds pretty impressive. What does that actually mean in this context, though?
All right, imagine you have this thing called a group ring. It's basically a way to combine a group and a ring into one structure. Now, universality means that any other skew field that sees the structure of this group ring can be mapped into the Linnell skew field, but in a way that preserves that structure. It's like the Linnell skew field is the central hub for all the other skew fields that are interested in that particular group ring.
Okay, that's a really helpful analogy. So
Yeah.
why is this universality so important for what the authors are doing in this paper?
Well, it allows them to link these things called L2 Betty numbers, which are usually calculated using analytical methods, to Betty numbers that they can actually calculate using these skew fields. It's like building a bridge between these two different mathematical worlds.
Right, so they're connecting these two different ways of looking at Betty numbers. How does that help them with their research? What are they getting out of that?
It lets them set up these inequalities between the L2 Betty numbers of different spaces, and then these inequalities actually lead to those vanishing results that we were talking about earlier, where certain L2 homology groups become 0 after they do those subdivisions.
It's really interesting how they're using these sort of abstract algebraic concepts to really drive these discoveries about the shape and properties of these mathematical spaces. It's a good
Yeah.
reminder that seemingly unrelated areas of math can be so deeply connected.
Absolutely. And let's not forget that the paper is particularly interested in the L2 homology of spaces built from those right-angled Coxeter groups, those mathematical kaleidoscopes we were talking about.
Right, the ones that we can visualize using that Davis complex. What technique did they use to actually study the L2 homology within that complex?
They use something called Mayer-Vietoris arguments. Remember that maze analogy from before?
Yeah.
It's like taking a complex space, breaking it down into these smaller pieces that overlap, and then looking at the homology of each piece and how they're all glued together. It's a way to analyze the whole thing by understanding its parts.
So they're applying this divide and conquer strategy to the Davis complex. How do they choose how to actually break it down?
They choose their decomposition very cleverly. They split the Davis complex along these subcomplexes that correspond to the mirrors in our kaleidoscope analogy.
Okay.
They're taking advantage of the way the right-angled Coxeter group is structured to make their analysis easier.
It's like they're carefully taking the kaleidoscope apart to see how each piece contributes to the overall pattern. What insights do they gain from taking this approach?
Well, choosing their decomposition this way lets them isolate how edge subdivisions actually affect the L2 homology. They show that subdividing an edge can sometimes cause certain homology groups to vanish, but leave others completely unchanged. It's a very precise way of seeing how those modifications impact the overall structure.
It's like they're performing surgery on the kaleidoscope, taking out specific parts and then seeing how that changes the pattern. Their control over the effects of these subdivisions is pretty impressive.
It is. And that precise control is what allows them to prove those main results, like those theorems 4.16 and 4.17 that we talked about. They basically establish when L2 homology vanishes for these specific types of spaces. It's like they're mapping out these regions in these mathematical landscapes where those holes just disappear.
And remember, this vanishing, it's not just some mathematical curiosity. This actually has real implications for understanding these broader conjectures, like the Singer conjecture, and how it relates to other conjectures, like the torsion concentration conjecture.
Absolutely. And speaking of that torsion concentration conjecture, remember, the authors actually found counterexamples to it.
Yes, that unexpected torsion growth outside of the middle dimension. That was a pretty big deal. It's like finding a secret passage in the maze where you least expected it. How did they actually find those counterexamples?
They did it by cleverly combining these edge subdivisions with a specific three-dimensional complex called AOL. This complex is really interesting because its L2 homology vanishes completely when you calculate it using rational coefficients. But it doesn't vanish in the top dimension when you use modulo p coefficients for some prime p.
So this complex has this sort of hidden homology that only shows up when you look at it through a specific mathematical lens.
Exactly. And by strategically embedding this complex into higher dimensional spheres and then doing those relative barycentric subdivisions, they can create spaces that actually violate the torsion concentration conjecture.
It's like they're planting this complex as a seed to grow these really exotic spaces with unexpected properties.
Yeah.
What's the significance of finding these counterexamples?
They really challenge our assumptions about how torsion growth actually works. They show that it's a lot more intricate than we might think at first, and that there are still these nuances and complexities that we need to untangle.
So basically, these findings are suggesting that there's still so much more to learn and explore in this area of mathematics. It really makes you wonder what other surprises are out there waiting to be found.
Well, that's the beauty of math, right? There's always something new to uncover. Remember our question from before about what happens if we go beyond barycentric subdivisions? Could exploring other types of subdivisions lead to even more unexpected results? The authors leave that as an open question, a challenge for us to keep digging.
It's pretty exciting to think about all that uncharted territory in these mathematical landscapes. Who knows what strange and amazing things are out there waiting to be discovered. This has been an incredible journey so far, but I have a feeling we're not quite done yet, are we?
You're right, there are a few more twists and turns left in this paper. We'll be back in part 3 to explore them together.
Welcome back. It's been quite a journey so far, exploring these right-angled Coxeter groups and their L2 homology. I have to say, all this talk about skew fields and subdivisions has my head spinning.
I get it. They can be tough to grasp, but sometimes a simple analogy can help. Think about a pretzel.
A pretzel. Okay, I'm listening.
How do you make a pretzel? You start with just a simple loop of dough, and then you twist it and fold it into that more intricate shape.
Yeah, I'm following along.
Now imagine that loop of dough is like a basic geometric shape, like a triangle, and all that twisting and folding, those are the operations we do to that shape, like the edge subdivisions we've been talking about.
So the more you twist and fold, the more complex the pretzel gets. Just like how barycentric subdivisions create those more intricate kaleidoscope patterns.
Exactly. And just like pretzels come in all sorts of complexities, so do our mathematical spaces. This paper focuses on a specific type of complexity measured by L2 homology.
Right, those holes in higher dimensions. And the authors showed how subdividing edges, which are like the twists and folds in our pretzel analogy, can actually make some of those holes vanish.
That's right. By understanding how those holes vanish, we gain these insights into the Singer conjecture. That's the one that predicts that the L2 homology of certain spaces should be 0, except for right in the middle dimension. It's all about getting at the fundamental structure of these spaces.
I see the analogy now. The holes in the pretzel represent the L2 homology, and the way we twist and fold the dough affects which holes disappear. That's a pretty delicious way to think about it.
It is. And don't forget, these math concepts, they have real-world applications too. You can use them to understand things like the shape of data sets or how complex systems behave, maybe even the structure of the universe itself.
Wow, now that's some food for thought. But let's get back to the paper. What about one of the most surprising findings, those counterexamples to the torsion concentration conjecture?
Yes, that unexpected torsion growth outside of the middle dimension, that was a big discovery. It's like finding a hole in your pretzel that you never even thought could exist.
Exactly. What makes these counterexamples so important? Why should we care?
They challenge our assumptions about how torsion growth actually behaves. They show that we need to think about different types of subdivisions when we're studying these spaces. Barycentric subdivisions are really useful, but as these counterexamples show, they don't tell the whole story.
So it's like we can't rely on just one tool. We need a whole set of techniques to really understand these complicated structures.
Precisely. The authors focused on barycentric subdivisions because they're really effective for understanding the L2 homology of right-angled Coxeter groups, but their counterexamples show that using other types of subdivisions, well, that could lead to even more fascinating insights.
It's like they've opened this door to a whole new world of math, and we're just beginning to explore it. This has been quite a journey.
It has. We've really dug deep into these right-angled Coxeter groups, their L2 homology, and how it all connects to things like edge subdivisions, the Singer conjecture, and even that torsion concentration conjecture.
We've learned about these Linnell skew fields, Mayer-Viator's arguments, and we've seen how even these tiny changes to these mathematical objects can have huge consequences. But I think the biggest takeaway is that math is alive. It's full of surprises and questions that we're still trying to figure out.
Couldn't have said it better myself. There's always more to discover.
So to all our listeners out there, keep exploring the world of math. You never know what amazing things you might find. This has been The Deep Dive. Thanks for joining us. All right, get ready to dive into a world where shapes meet algebra.
It's a place where we can use things like subdivisions to unlock secrets about geometric structures.
And maybe even solve some age-old mathematical mysteries along the way, right?
Exactly.
Well, you've brought a fantastic paper for us to unpack today.
Oh, it's a good one?
Edge subdivisions and the L2 homology of right-angled Coxeter groups by Avramidi, Okun, and Schreve.
It's brand new, just came out this week.
Hot off the presses. And we're going to go through it together, page by page, equation by equation.
And because you, our listener, are already familiar with this area,
we can really get into the details of the proofs.
the logic behind what the authors found.
So let's set the stage.
Sounds good.
The paper starts with a nice introduction, outlining the key players in this whole mathematical drama.
Right.
We've got right-angled Coxeter groups, L2 homology, Singer's conjecture, and Davis complexes all connected in some way.
Like a big web.
Now, I think it's worth pointing out why right-angled Coxeter groups are so interesting to mathematicians.
Oh, absolutely. They pop up in so many different areas of math.
I was going to say, it's not just one little corner of mathematics.
Yeah. No, not at all. From studying symmetries in geometric shapes to analyzing networks.
Like in computer science, even.
Even there, yeah. Their influence is really broad.
It is, and L2 homology gives us a powerful tool to examine these groups.
It's like having a high-powered lens.
A way to measure the holes in the spaces connected to them.
But in a much more refined way than traditional homology.
More detail, like a higher resolution image.
Exactly. And then we have Singer's conjecture looming over all of this.
A big unsolved problem in topology.
A major one. It suggests that L2 homology should vanish in certain dimensions for specific types of spaces.
And that conjecture really drives a lot of research in this area.
This paper included.
Now, the authors focus on Davis complexes,
A specific type of space.
which gives us a concrete way to represent a right-angled Coxeter group geometrically.
It's like a blueprint for building a shape based on the group structure.
And their big innovation is using edge subdivisions
A technique for breaking down the Davis complex.
into smaller, more manageable pieces,
And they're particularly interested in barycentric subdivision.
which, if I remember correctly, is a method that maintains much of the original symmetry of the complex.
Yes, that's right.
It's like taking a mosaic and carefully dividing each tile into smaller, identical pieces, right?
A perfect analogy. The overall pattern stays the same.
But you can see the finer details more clearly.
Exactly. And this is where things get really interesting.
Because by doing these subdivisions, they gain a deeper understanding of how L2 homology behaves.
A much deeper understanding.
Now, the heart of this paper is Theorem 1.1,
It's right there on page 2.
making a bold statement. Under certain conditions, subdividing the edges of a Davis complex will either keep the L2 homology the same in specific dimensions or make it completely disappear.
Vanish. Poof. Gone.
And this is a big deal because it suggests that subdivision can really simplify how we analyze L2 homology.
And maybe even help us crack Singer's conjecture.
Now, the theorem has two parts to it,
Two sides of the same coin.
each dealing with a different type of Davis complex.
The first part looks at complexes built from the barycentric subdivision of the boundary of an n-simplex.
Okay, let's break that down a bit.
Sure.
An n-simplex is basically like a triangle.
But in higher dimensions.
Right, so a 2-simplex is your regular triangle, a 3-simplex is a tetrahedron, and so on.
Exactly. And the boundary of an n-simplex is like the skeleton of the shape, just the edges and vertices.
And the barycentric subdivision adds points in the middle of all the edges, faces, and so on.
So you're adding more points, making it more intricate.
So the first part of the theorem is saying that if you build a Davis complex using this kind of subdivided shape.
Then Singer's conjecture holds true.
Okay, that makes sense.
The second part of the theorem takes this further, looking at Davis complexes built from barycentric subdivisions of any triangulation of a sphere.
But only in even dimensions, right?
That's right. So we're talking about spheres in 4 dimensions, 6 dimensions, 8 dimensions, and so on.
And these spheres are broken down into those simpler triangular pieces.
Triangulated, yes.
And the theorem says that even in these complex, higher dimensional cases, subdividing still preserves those crucial L2 homology properties.
It's like subdivision smooths things out, revealing underlying structures that might be hidden in the original complex.
Okay, so we've set the stage, we've got our players.
Now let's get into the real action.
The proof. The authors use a mix of techniques.
Induction, clever manipulation of geometry and algebra.
A little mathematical magic, perhaps?
Oh, definitely. A key insight they have is that removing an edge from a Davis complex has the same effect on L2 homology as subdividing that edge.
It's like realizing you can achieve the same look in a mosaic by either removing a tile or dividing it into smaller pieces.
The overall pattern changes in a similar way,
And this lets them use a powerful tool called the Mayer-Vietoris sequence.
which is a way to break down a complex problem into smaller, more manageable pieces.
Like a detective piecing together clues at a crime scene.
Exactly. They apply the sequence over and over,
Simplifying the Davis complex step by step.
carefully tracking how the L2 homology changes along the way,
It's like playing a game of Jenga.
carefully removing pieces without making the whole tower collapse.
And the authors are so skillful at manipulating the geometry and algebra of these spaces,
They exploit the inherent symmetries of those barycentric subdivisions.
showing that some parts of the Davis complex don't contribute anything to the L2 homology in certain dimensions,
They're not just breaking the problem down, they're streamlining the whole process,
identifying and discarding irrelevant information.
leading them to a really elegant proof of Theorem 1.1.
A masterpiece of mathematical precision.
Absolutely.
Now, on page 7, they introduce the concept of virtual acyclic
Right.
and give a proof for proposition 4.1.
They define a group as virtually acyclic if its L2 Betty numbers are all 0.
Okay.
And then they show that for any right-angled Coxeter group, its associated Heck-von Neumann algebra, when you combine it with the field of rational numbers, is virtually acyclic.
They use induction to prove this, right?
Yes, and by analyzing the specific structure of these algebras.
And that result ties the algebraic properties of the Heck-von Neumann algebra to the geometric properties of the Davis complex.
It's a fascinating connection.
It is. And then they go on to show that the same result holds even when considering the algebra tensored with a field of characteristic P.
As long as the prime P doesn't divide the order of any finite subgroup of the Coxeter group.
That's proposition 4.2 on the same page.
Right?
And this expansion to fields of characteristic P seems like a big deal.
It hints at a deeper link between prime numbers and the L2 homology of these spaces.
I'm sensing a pattern here, always pushing further, looking deeper.
And that leads us right into the world of skew fields, which is a more general algebraic structure.
And that's where we'll pick up in the next part of our deep dive.
Things are going to get even more interesting, so stay tuned.
I can't wait.
Buckle up, because we're entering a realm where the rules of arithmetic get a little bit, well, twisted.
Oh, I'm intrigued. Last time we left off with the promise of exploring skew fields.
Right.
A concept that sounds kind of intimidating, I have to admit.
They're not as scary as the name might suggest. Think of them as generalizations of the number systems we're all familiar with.
Like real numbers, rational numbers, those sorts of things.
Exactly. We can still add, subtract, multiply, and divide.
So far, so good.
But there's a catch.
Uh-oh. I knew there had to be a twist.
The order in which you multiply can actually change the outcome.
Wait, so in a skew field, 2 times 3 might not be the same as 3 times 2.
You got it. It's this non-commutativity that makes skew fields so powerful.
My brain's doing a little backflip right now, but I think I get it.
They let us capture more complex relationships, symmetries that we just couldn't with ordinary numbers.
Like adding a whole new dimension to our mathematical toolbox.
Exactly. And it makes sense when we're talking about right-angled Coxeter groups and Davis complexes, right?
Yeah, all those intricate symmetries and relationships.
It seems we need a more, shall we say, sophisticated algebraic framework to really study them.
I'm following you. And that's where Linnell skew fields come in.
Named after the mathematician Peter Linnell.
Well, that's the one. These skew fields are especially useful when studying L2 homology.
Now, on page 8, they define a Linnell skew field.
Yeah.
It has a valuation function that meets a certain growth condition.
Right. It says that the valuation of a product of elements is bounded by the product of the valuations of the individual elements.
Okay.
But only up to a constant factor, and that factor depends on how many elements are being multiplied.
I see.
And this specific property is what links the world of Linnell skew fields with the world of Davis complexes.
The bridge between algebra and geometry.
Exactly. Let's think back to those Davis complexes for a minute.
Those intricate structures built by gluing simpler shapes together.
No, the instructions for how those pieces are glued together, we can actually encode those using matrices.
Matrices. Those spreadsheets for mathematicians.
Haha, that's one way to put it. And here's the key. We can think of matrices as elements within a skew field.
So we can shift from a geometric problem studying L2 homology of a Davis complex to an algebraic problem of analyzing matrices within a Linnell skew field.
Now you're getting it. It's like translating from one language to another.
And the authors show that the L2 homology of the Davis complex is closely tied to the properties of certain matrices in the Linnell skew field.
Which is crucial for proving their main results, including theorem 1.1 that we talked about before.
Right. Now, on page 9, they introduce proposition 5.2.
Yes.
It seems to connect the vanishing of L2 homology to certain elements existing in the Linnell skew field.
It's a cornerstone of their whole approach.
It states that if the L2 homology of a Davis complex disappears in a certain dimension,
Vanna is, yes.
then there are specific elements in the associated Linnell skew field that satisfy a particular equation.
That's it. And those elements, they're labeled as bi.
They're constructed using the matrices that represent the boundary maps in the chain complex linked to the Davis complex, right?
Precisely. And that equation they satisfy, the sum of bi times the boundary map I equals 0, that reflects how the Davis complex is structured.
Particularly how those boundaries of the simplices are glued together.
You're getting it. They're essentially translating geometric relationships into algebraic equations.
Moving from the world of shapes to the world of equations.
Exactly. And that translation is critical for their proof.
It allows them to really leverage those Linnell skew field properties.
To manipulate equations and ultimately show that the vanishing L2 homology places restrictions on how the Davis context can be structured.
So they're using algebra to reveal hidden secrets about geometry.
That's a great way to think about it. Then they move on to explore a specific family of Davis complexes, denoted as XL.
These are linked to flag triangulations of even-dimensional spheres, if I'm reading this correctly.
Yes, and they're especially interesting because of their properties related to L2 homology and subdivision.
They have theorem 5.3 on page 10.
Right.
That seems to connect the vanishing L2 homology for XL to the existence of certain solutions in the Linnell skew field.
Theorem 5.3 says that if the reduced L2 homology of XL vanishes in certain dimensions, it's the same as saying there are solutions to a specific set of equations in the associated Linnell skew field.
And those equations use those bi-elements we talked about earlier, along with the matrices for the face maps in the chain complex of XL.
It's all connected. This equivalence gives us a really powerful tool for analyzing the L2 homology of these particular Davis complexes.
So we can understand the topology of XL by looking at the algebra of certain equations in the Linnell skew field.
You've got it. And they use this to prove several key results, including the vanishing of L2 homology in specific dimensions for certain families of XL.
Nice. Now, on page 11, they introduce this concept of depth. for an element in a right-angled Coxeter group.
The depth of an element sort of tells you how far it is from the identity element.
So the identity element is like the starting point.
You could say that...
And depth is like how many steps it takes to get to that element from the starting point.
Exactly. It's defined as the shortest way to express that element as a product of the group's generators.
So the depth of an element gives us a sense of its complexity within the group structure.
That's the idea. And the authors use this concept to prove lemma 5.4. which sets a limit on the depth of certain elements in the Coxeter group that's associated with XL.
And this limit, this bound, is essential for analyzing the L2 homology of XL further on.
Absolutely. They're carefully building a chain of results here, each one relying on what came before.
Like a carefully constructed argument, brick by brick.
It's a hallmark of rigorous mathematical proof, making sure each step is solid.
This is really impressive work. But before we jump to the next part, where they actually build those counterexamples to the torsion concentration conjecture.
Right.
I have a question.
Shoot.
It's amazing how seamlessly they blend geometry and algebra throughout this paper.
It is, isn't it?
It's like they're constantly shifting perspective, looking at the same objects through different lenses.
Two sides of the same coin.
But how do they keep things so clear and coherent with all this switching back and forth?
I think it comes down to a deep understanding of those underlying mathematical structures.
Okay.
And a mastery of the tools of both geometry and algebra.
They see the connections between these seemingly different fields.
And they use those connections to their advantage, revealing insights you wouldn't see otherwise.
It's like they're fluent in two languages.
Translating effortlessly between them.
And that's what makes this research so compelling.
Absolutely.
Okay, I'm ready to see where this mathematical journey takes us next.
On to part 3 then. Get ready for a twist because we're about to encounter some surprising counterexamples.
Oh, I love a good mathematical mystery.
These challenge a long-standing conjecture.
Okay, I'm all ears.
Last time we were deep in the world of Linnell's skew fields.
Right, and how they can help us understand those geometric properties of Davis complexes.
But now we're going to see some assumptions challenged.
Ooh, sounds exciting.
We're going to see how the authors construct specific Davis complexes that actually contradict the torsion concentration conjecture.
Okay, remind me what that conjecture says again.
It proposes a relationship between how torsion elements grow in a group and its L2 homology.
Okay, got it. So on page 13, they jump right into building these counterexamples.
Right into it.
And they start with this three-dimensional shape called OL.
Yeah.
What's so special about this OL thing?
Well, it has a really peculiar property.
Okay, tell me.
Its L2 homology completely vanishes when you calculate it using rational numbers.
It just disappears.
Poof, gone.
Okay.
But if you use a finite field, like the integers modulo, a prime number...
It doesn't vanish.
Nope, it sticks around.
So the choice of number system actually affects the L2 homology.
It does. It's pretty fascinating, right?
Yeah, it's like those abstract algebraic choices have a real impact on how we understand these geometric objects.
Exactly, and that's what the authors use to build their counterexamples.
So how do they use OL to challenge that torsion concentration conjecture?
Okay, so they cleverly embed OL into a triangulation of a 6-dimensional sphere.
6 dimensions, wow.
Then they do a relative barycentric subdivision.
Meaning?
They subdivide everything except OL itself.
Ah, so they're being very strategic about which parts of the shape get subdivided.
Absolutely. It's key to creating that counterexample.
Got it.
This specific construction, it creates a Davis complex where the torsion concentration conjecture predicts 0 torsion growth in dimension 6. Because of how OL behaves...
They show that the torsion growth is actually not 0.
You got it. It's non-zero.
It's like they set a trap for the conjecture.
In a way, yes.
Right.
They created a scenario where the conjecture's prediction just doesn't match up with what's really happening.
That's clever.
And it's not just a one-time thing. They can create similar counterexamples in even higher dimensions.
Like 14 and 21, I see that here.
They do that by taking joins of this initial construction.
Joins, those are like,
It's a way to combine two shapes.
Okay.
Imagine connecting every point in one shape to every point in another shape.
Okay, I can picture that.
The resulting object is the join of those two shapes.
So they're basically scaling up their counterexample.
To higher dimensions, showing that the torsion concentration conjecture, at least as it's currently stated, needs some work.
It needs to be refined, maybe.
Exactly. It needs to account for these new cases they've discovered.
This is groundbreaking stuff. It highlights how intertwined algebra, geometry, and topology really are.
It is.
And it reminds us that even in well-established areas of math, there are always new things to discover.
Always new mysteries to uncover.
These counterexamples, they open up so many new questions,
New avenues for research.
forcing us to rethink our understanding of L2 homology and torsion growth.
Absolutely.
This deep dive has been incredible. We've gone from complex geometric structures to abstract skew fields. Witness the power of mathematical proof.
It's been quite a journey.
The authors of this paper have made a real contribution to the field.
A significant one.
I have no doubt their work will inspire a lot of future mathematicians.
To push the boundaries even further.
And to our listeners, if you want to explore this fascinating world more deeply,
We'll include links to the paper and other resources in the show notes.
so be sure to check those out.
Remember, the pursuit of mathematical knowledge never really ends.
It's an ongoing adventure.
Every new discovery, every unexpected twist, it just keeps things exciting.
That's what makes it so fun.
So keep those minds curious.
And until next time,
Happy exploring!
all right, let's jump into this paper on edge subdivisions and L2 homology of right-angle Coxeter groups.
Yeah, sounds good.
It looks like it really gets into some pretty fascinating territory with the Singer conjecture,
It does.
and even ventures into torsion growth.
Yeah.
So to start off,
Mm-hmm.
they set the stage by reminding us about the Davis complex,
Right.
denoted lateral associated with the flag complex L.
Yeah.
It's built by taking simplices for each complete subgraph and gluing them together based on shared faces.
Exactly. And they quickly point out a key fact.
Okay.
That the link of a vertex in this Davis complex is homotopy equivalent to the suspension of the link of the corresponding vertex in the original flag complex.
Okay, so let's unpack that a bit.
Okay.
We're dealing with two different links here.
Mm-hmm.
One in the Davis complex and one in the original flag complex.
Yes.
And they're saying these links are related through this idea of suspension,
Right.
which is like taking a space and stretching it out into a higher dimension by adding two new points and connecting everything to those points.
Exactly. And this homotopy equivalence
Okay.
means that while the links might look different geometrically, they share the same fundamental topological properties.
I see.
So understanding the link in the flag complex can give us valuable information about the corresponding link in the Davis complex and vice versa.
Okay, now they dive into this idea of skew fields, which seem to be a central tool for their approach.
Mm-hmm.
They even give a specific example, the Linnell skew field,
Right.
denoted DFG, associated with a group G in a field F.
Yes.
They mentioned it has this interesting property where the group ring FG embeds into it.
Yes. The Linnell skew field is going to be crucial for their analysis of L2 Betty numbers.
Okay.
And the fact that the group ring embeds into it allows them to leverage tools from ring theory to study these Betty numbers.
Okay, I'm with you so far.
Okay.
Now, the introduced lemma 2.1, which deals with equivariant homology with coefficients in a skew field.
Mm-hmm.
It looks a bit technical,
Yeah.
but it seems to be setting up some fundamental machinery for their analysis.
Absolutely. Lemma 2.1 is establishing a long exact sequence for equivariant homology,
Okay.
which is a powerful tool for understanding how homology groups behave under certain transformations.
So it's like a mathematical chain reaction.
Yes.
Where changes in one part of the complex ripple through to other parts.
Mhm.
And this long exact sequence helps us track those changes systematically.
That's a great way to think about it. And they immediately follow this up with Lemma 2.2,
Okay.
which gives us another powerful tool,
Okay.
the Mayer-Vietoris sequence.
Ah, the Mayer-Vietoris sequence.
Again, for equivariant homology with skew field coefficient.
It's like a divide and conquer strategy for understanding the homology of a space by breaking it down into smaller, more manageable pieces.
Exactly. And this lemma allows them to apply that strategy in the context of equivariant homology with skew field coefficients, which is precisely the setting they need for analyzing the L2 homology of these Davis complexes.
Okay, so they're building up a powerful toolbox here,
Yeah.
equipping themselves with the right tools to dissect these complex mathematical objects.
Mhm.
Now they introduce this idea of the FL2 Betty numbers of a GCW complex X,
Right.
denoted BFPSG.
Yes.
It seems to be a way to measure the size of those holes in the space.
Yeah. But using coefficients from the field F.
Precisely, FL2 Betti numbers generalize the concept of L2 Betti numbers,
Okay.
allowing us to refine our understanding of those holes by considering homology with coefficients in a specific field F.
Okay.
This added flexibility will be crucial for their later analysis of torsion growth.
I'm seeing how these different pieces are starting to fit together.
Yeah.
Now they present lemma 2.4,
Mm-hmm.
which deals with this concept of induction.
Right.
They're saying that if we have a subgroup H of G,
Okay.
the FL2 Betti numbers calculated using the smaller group H can be related to the FL2 Betti numbers calculated using the larger group G.
Yes. Lemma 2.4 is establishing a crucial connection between the FL2 Betti numbers of a space X viewed as a G space.
And the FL2 Betti numbers of the same space viewed as an H space.
So it's like zooming in and out of the space,
Yeah.
observing how the holes appear from different perspectives.
Mm.
And this lemma gives us a way to connect those different views.
That's a great analogy. And they immediately apply this lemma to prove theorem 2.5, which connects L2 Betti numbers to homology growth.
Homology growth. That sounds intriguing.
Providing a formula for calculating those Betti numbers using a limit involving the ranks of homology groups with coefficients in a field F.
It seems to be a way to measure how the complexity of the homology groups changes as we consider larger and larger subgroups of our main group.
Exactly. Theorem 2.5 gives us a way to quantify that complexity
Okay.
and relate it to the L2 Betti numbers, which are our primary tool for understanding the holes in these spaces.
This is really fascinating.
Yeah.
They're connecting these seemingly disparate concepts, L2 Betti numbers and homology growth, in a way that illuminates the deep structure of these mathematical objects.
I completely agree, and they don't stop there. Lemma 2.6 establishes an inequality relating the L2 Betti numbers calculated using different groups, providing a bound that will be useful for their later analysis.
It's like they're building a mathematical fence around those L2 Betti numbers,
Yeah.
constraining their behavior and allowing for more precise calculations.
That's a great way to visualize it, and this control over the L2 Betti numbers is going to be crucial for proving their main results.
Okay.
Now, they present theorem 2.7,
Okay.
which provides a more refined formula for calculating L2 Betti numbers, specifically when we're working with finite fields.
Finite fields. Those are like the building blocks of many algebraic structures.
Right.
So understanding how L2 Betti numbers behave in this setting is likely to have far-reaching implications.
You're absolutely right, and theorem 2.7 gives us a powerful tool for analyzing those Betti numbers in this important special case.
Okay.
They then introduce the Kuhneth formula for L2 homology,
Okay.
a powerful tool that allows us to break down the L2 homology of product spaces into the L2 homology of their individual components.
The Kuhneth formula. It's like a mathematical recipe that tells us how to combine ingredients to create a more complex dish.
Okay.
In this case, the ingredients are the L2 homology groups of the individual spaces,
Yes.
and the dish is the L2 homology of their product.
That's a delicious analogy.
Uh-huh.
And this recipe will be crucial for understanding the L2 homology of more complex spaces built up from simpler components.
Now, after laying all of this groundwork,
Yes.
they finally delve into the world of right-angled Coxeter groups,
Mm-hmm.
or RACGs.
Right.
And they start off by defining what makes these groups so special.
Okay.
They're generated by elements of order 2,
Mm-hmm.
meaning that each generator, when applied twice, brings us back to the starting point.
Right.
And the only relations between generators are commutation relations,
Yes.
meaning that the order in which we apply certain generators doesn't affect the outcome.
This simple set of rules leads to a surprisingly rich and complex structure. And the authors are interested in understanding how this structure is reflected in the L2 homology of the associated Davis complexes.
Okay, so we've got these RACGs with their simple rules,
Yeah.
and we've got their associated Davis complexes,
Right.
which capture the geometric structure of these groups.
Mm-hmm.
Where do they go from here?
They start exploring the behavior of FL2 Betti numbers when we manipulate the underlying RACG.
Okay.
And they focus on two key operations,
All right.
removing vertices
Okay.
and removing edges from the flag complex that defines the RACG.
So it's like we're playing with the building blocks of the RACG,
Yes.
seeing how those changes affect the overall shape of the Davis complex and, consequently, its L2 homology.
Yeah.
Clever.
And lemma 3.2 provides a crucial insight.
Okay.
If we remove a vertex whose link is FL2 acyclic,
Mhm.
meaning it has no holes from the perspective of L2 homology with coefficients in F,
Okay.
then removing that vertex won't change the overall FL2 Betti numbers of the Davis complex.
It's like removing a piece of a puzzle that doesn't affect the overall picture.
Yeah.
The remaining pieces still fit together perfectly.
Right.
And the image remains intact.
But things get more interesting when they start removing edges instead of vertices.
Okay.
This is where Theorem 3.3 comes in.
Okay.
And it's one of the key innovations of this paper.
I remember we touched on this earlier.
Yes.
Removing edges is trickier than removing vertices because it can create a non-full subcomplex.
Precisely.
Meaning we're not just removing a piece of the puzzle,
Right.
we're potentially breaking connections between the remaining pieces.
And this breaking of connections can make the analysis of L2 homology more challenging.
Right.
But Theorem 3.3 provides a way to navigate this complexity.
Okay.
It essentially says that if the link of the removed edge is FL2 acyclic in a specific dimension,
Okay.
then removing that edge won't increase the FL2 Betty number in that dimension for the Davis complex.
So even though we're breaking connections, as long as those connections don't introduce any new holes in a particular dimension,
Yes.
we can still control the L2 homology.
Exactly. And this control is key to their approach.
Okay.
They now introduce this concept of edge subdivisions,
Okay.
which is going to play a central role in their analysis.
Right.
Lemma 4.3 provides the link between edge removal and edge subdivisions.
Okay.
It states that removing an edge is, from the viewpoint of FL2 Betty numbers, equivalent to subdividing that edge and then removing the newly created midpoint vertex.
Hold on. Let's break that down.
Okay.
We're saying that instead of directly removing an edge,
Yes.
which could disrupt the L2 homology in unpredictable ways,
Mm-hmm.
we can subdivide it by adding a new vertex in the middle.
Right.
And then, because the link of this new vertex has nice properties,
Yes.
we can safely remove it without altering the FL2 Betty numbers.
That's exactly right.
This is ingenious.
It's a clever trick that allows them to manipulate the complex while preserving the essential information about the L2 homology.
It's like a mathematical sleight of hand,
Mhm.
making those edges disappear without a trace.
Precisely. And this leads them to corollary 4.4,
Okay.
which says that if we start with a flag complex whose Davis complex has vanishing FL2 homology in a particular dimension, and we subdivide an edge whose link is also FL2 acyclic in the appropriate dimension, then the Davis complex of the subdivided complex will also have vanishing FL2 homology in that dimension.
So it's a way to preserve those hole-free dimensions as we reshape the complex through edge subdivisions.
Exactly. And this preservation property is key to proving some of the main results of this paper.
Okay.
They then take this idea further and consider iterated edge subdivisions.
Okay, so instead of just subdividing an edge once,
Yeah.
we can keep subdividing the resulting edges,
Mm-hmm.
creating a cascade of new vertices and reshaping the complex in intricate ways. It's like taking a simple line drawing and transforming it into a complex, multifaceted artwork
Yeah.
through a series of carefully chosen additions.
That's a beautiful analogy. And corollary 4.5 tells us that under certain conditions, these iterated edge subdivisions will preserve the vanishing of FL2 homology in specific dimensions.
Okay.
This leads to a remarkable result in corollary 4.6,
Right.
that the Davis complex associated with the barycentric subdivision of the boundary of an even-dimensional simplex has vanishing FL2 homology in all dimensions above the middle dimension.
Okay, let's unpack that a bit.
Okay.
Barycentric subdivision, if I recall correctly, is like adding a new vertex in the center of each simplex and connecting it to all the existing vertices.
Exactly.
And they're applying this to the boundary of an even-dimensional simplex, which is like taking a higher dimensional triangle and focusing on its edges and faces.
And they're saying that the Davis complex associated with the subdivided boundary has no holes in the higher dimensions.
Fascinating.
Yeah.
It suggests that there's a certain symmetry or balance in the L2 homology of these spaces.
I agree. And corollary 4.7 takes this idea even further.
Okay.
It shows that if we start with the triangulation of a sphere whose Davis complex satisfies the Singer conjecture,
Okay.
meaning it only has holes in the middle dimension,
Right.
and we apply any iterated edge subdivision to this triangulation, then the resulting Davis complex will still satisfy the Singer conjecture.
So it's like saying that these edge subdivisions, no matter how complex they get,
Yeah.
can't disrupt the fundamental balance of holes in these spaces.
Right.
The Singer conjecture, which predicts this balance, remains intact.
Precisely.
Now, to prove these results, they introduce a powerful new tool, relative barycentric subdivisions.
Yes.
Okay, I'm intrigued.
It's like taking the concept of barycentric subdivision and making it more targeted and flexible.
How do these relative barycentric subdivisions differ from the regular ones?
Instead of subdividing every simplex in the complex, we can choose specific subcomplexes to subdivide.
Interesting.
This gives us more control over how we reshape the complex
Okay.
and allows us to analyze its L2 homology in a more nuanced way.
It's like we're performing a delicate surgery on the complex, carefully reshaping it without disrupting its vital functions.
That's a great analogy, and Lemma 4.8 provides the mathematical framework for understanding how the links of vertices behave in these relative barycentric subdivisions. It tells us that the link of a newly created vertex in a relative barycentric subdivision is determined by the specific subcomplex we're subdividing.
So it's like saying that the new vertex's neighborhood depends on which part of the complex we're focusing on.
Exactly, and understanding these links is crucial for analyzing how relative barycentric subdivisions affect the overall L2 homology of the Davis complex.
Okay, I'm following so far.
Yeah.
But how do they actually use these relative barycentric subdivisions to simplify their calculations?
They cleverly relate relative barycentric subdivisions to the more familiar concept of edge subdivisions. Lemma 4.9 establishes this connection by showing that a specific type of relative barycentric subdivision where we cone off a subcomplex by adding a new vertex and connecting it to every vertex in that subcomplex can be achieved through a sequence of edge subdivisions.
So instead of directly introducing this new vertex with all its connections, we can build up that structure step by step through a series of edge subdivisions.
Precisely. And this realization is key to proving Lemma 4.11, which extends this connection to more general relative barycentric subdivisions. It shows that any relative barycentric subdivision can be achieved through a sequence of edge subdivisions.
This is really clever.
Demonstrating the power and flexibility of this approach.
They're essentially building a bridge between relative barycentric subdivisions and edge subdivisions, allowing them to leverage the tools they've developed for analyzing edge subdivisions to understand these more complex relative subdivisions.
Exactly. And this bridge leads them to Lemma 4.12, which establishes a hierarchical relationship between different relative barycentric subdivisions. It tells us that if we have a chain of nested flag subcomplexes, the relative barycentric subdivision with respect to the smallest subcomplex can be obtained through a sequence of edge subdivisions, starting from the relative barycentric subdivision with respect to the larger subcomplex.
So it's like zooming in on the complex, focusing on smaller and smaller subcomplexes. And this lemma tells us how those different levels of focus are related through edge subdivisions.
That's a great way to visualize it.
And this hierarchical relationship is key to understanding how relative barycentric subdivisions interact with each other and how they affect the overall L2 homology of the Davis complex. I'm really impressed with the level of detail and ingenuity in their approach. It's like they're carefully crafting a delicate mathematical tapestry, weaving together these different concepts to create a beautiful and intricate pattern.
I completely agree. Now, they bring all of these ideas together in Theorem 4.13, which provides a concrete way to construct a relative barycentric subdivision, the boundary of a simplex, through a sequence of edge subdivisions starting from a specific type of suspension.
Suspensions, relative barycentric subdivisions, edge subdivisions, it's all coming together.
It is.
So they're saying that we can build up this complex relative barycentric subdivision of the boundary through a series of edge subdivisions, starting from this stretched out lower dimensional structure.
Exactly. And this construction is a key ingredient in proving their main results about the L2 homology of these spaces. They combine this construction with their earlier results about the preservation of vanishing FL2 homology under edge subdivisions to prove corollary 4.14. It shows that any relative barycentric subdivision of the boundary of a simplex can be constructed as an iterated edge subdivision of the boundary of an octahedron.
An octahedron that's like a three-dimensional diamond shape, And they're saying that we can transform any relative barycentric subdivision of a simplex's boundary into the boundary of this diamond shape through a series of edge subdivisions. Why is this transformation so important?
It's crucial because the boundary of an octahedron has a very special property. Its Davis complex is FL2 acyclic. By connecting relative barycentric subdivisions to this hole-free octahedron boundary. They can make powerful statements about the L2 homology of these more complex subdivisions. This leads them to one of their main results, Theorem 4.16. The Davis complex associated with any relative barycentric subdivision of the boundary of an odd-dimensional simplex is also FL2 acyclic.
Wow, they've taken us on quite a journey.
Yeah.
They've built a whole theory around these edge subdivisions, barycentric subdivisions, and relative barycentric subdivisions, culminating in this powerful result about the L2 homology of these spaces.
It is a powerful result.
It's amazing how they've managed to maintain control over the FL2 homology throughout these complex manipulations.
It's a testament to their deep understanding of these concepts and their ability to weave together seemingly disparate ideas to create a coherent and elegant theory.
I can't wait to see where they take us next.
Yeah.
This is just the beginning of their exploration.
Right.
And I have a feeling there are many more surprises in store.
I agree. This paper is full of surprises.
Okay.
Let's take a break here and pick up where we left off in our next session.
Sounds good.
Picking up where we left off, the authors now shift their focus from FL2 acyclicity to general FL2 Betty numbers.
Okay, so instead of just looking for the absence of holes, they're now interested in quantifying the size of those holes using these FL2 Betty number.
Exactly. Theorem 4.17 provides a key insight into how these numbers behave under relative barycentric subdivisions.
Okay.
It states that in many cases, applying such a subdivision doesn't change the FL2 Betty numbers above a certain dimension, and it can only decrease the FL2 Betty number in that critical dimension.
So it's like saying these subdivisions can smooth out some of the smaller holes, but can't create any new larger ones above a certain threshold.
That's a great way to put it. And this smoothing effect is crucial for proving corollary 4.18, which establishes the vanishing of certain L2 Betty numbers for Davis complexes associated with barycentric subdivisions of triangulations of spheres.
Spheres, those perfectly symmetrical objects that have always captivated mathematicians.
Right.
It seems like they're finding a kind of symmetry in the L2 homology of these spaces as well.
Precisely. Corollary 4.18 demonstrates that the Davis complexes associated with specific subdivisions of spheres exhibit a particular kind of balance in their L2 homology, with certain Betty numbers vanishing due to the smoothing effects of those subdivisions.
It's fascinating how they're connecting the geometric symmetry of spheres to the algebraic properties of L2 homology through these carefully constructed subdivisions.
Absolutely. And remark 4.19 broadens the scope even further, extending this result to generalized homology spheres.
So their results apply to a wider class of spaces that share key topological features with spheres.
Yes. This highlights the wide-reaching implications of their findings beyond perfectly symmetrical spheres.
That's impressive.
Now the paper takes an intriguing turn, applying these insights to the problem of torsion growth in groups. You might recall our earlier discussion about the torsion concentration conjecture.
Yes, I remember it predicted a specific behavior for torsion growth in certain groups.
Right. Well, the authors make a remarkable discovery. They find counterexamples to this conjecture.
Wow, that's huge. So they're challenging a long-held mathematical belief.
They certainly are, and they provide explicit examples of triangulations of higher dimensional spheres that violate the torsion concentration conjecture.
That's going to send shockwaves through the mathematical community. But how do they actually construct these counterexamples? It seems like a monumental task.
It all starts in section 5, where they delve into the intricate relationship between universal coefficients, torsion growth, and L2 Betty numbers.
Right. Universal coefficients provide a bridge between different types of homology groups.
Exactly.
Relating those with coefficients in a field F to those with integer coefficients.
Lemma 5.1 utilizes this bridge to establish a crucial inequality. If the L2 Betty numbers of a group meet a certain condition, then its torsion growth must also satisfy a corresponding condition.
So the size of the holes, as measured by the L2 Betty numbers, can constrain the amount of twisting allowed in the group.
Precisely. And this connection is key to constructing their counterexamples.
I'm starting to see the pieces fall into place.
Yeah.
They're using their knowledge of L2 homology to manipulate torsion growth and ultimately find those surprising counterexamples.
Exactly. Corollary 5.2 builds upon this connection. Providing specific conditions that guarantee the existence of torsion growth in certain dimensions for groups associated with relative barycentric subdivisions.
So by carefully choosing these subdivisions,
yes,
they can force the groups to exhibit a certain amount of torsion growth, leading to a violation of the torsion concentration conjecture.
That's the crux of their strategy. It's a beautiful example of how seemingly abstract concepts can be interwoven to challenge established mathematical ideas.
This paper is full of unexpected twists and turns.
It is.
It's like a mathematical detective story where they're using their tools and ingenuity to uncover hidden truths.
I love that analogy, and the story doesn't end there.
Okay.
In section 6, they take a detour and apply their earlier result, theorem 3.3,
Okay.
about removing edges with FL2 as cyclic links,
Right.
to a class of complexes called minimally branching complexes.
Minimally branching complexes, those are the ones where the splitting of the structure is minimized.
Yes. Theorem 6.1 states that the Davis complexes of these minimally branching complexes have vanishing FL2 homology in the top dimension,
Right? Okay.
unless the complex is a specific type of join,
Okay.
the n-fold join of 3 points.
So these complexes have a certain rigidity to their structure,
Right.
which is reflected in the vanishing of their top-dimensional FL2 homology.
Precisely, and this rigidity is a direct consequence of their earlier findings about edge removal,
Okay.
showcasing the far-reaching impact of their work. It's amazing how they've connected these seemingly disparate concepts,
Yeah.
edge removal and the geometry of minimally branching complexes,
Right.
to reveal something new about the structure of these spaces.
This paper is a treasure trove of mathematical insights.
It is.
They've taken us on a journey through L2 homology, edge subdivisions,
Yeah.
barycentric subdivisions,
Right.
torsion growth, and now minimally branching complexes.
It is quite a journey.
Each step has built upon the previous one,
Yes.
culminating in a deeper understanding of these intricate structures.
I couldn't agree more. It's a testament to their creativity and ingenuity, but the journey isn't over yet.
Okay.
They have even more to reveal about their groundbreaking findings. Shall we delve into the final chapter of this mathematical adventure?
Absolutely lead the way. I'm eager to see what other surprises they have in store. All right, ready to uncover those final surprises?
Yeah, let's dive in. The authors now turn their attention to specific examples and applications of their results, starting with a closer look at the Singer conjecture.
Okay, the Singer conjecture, that's the one predicting non-zero L2 Betty numbers only in the middle dimension for certain spaces, right?
Exactly. And in proposition 5.3, they verify this conjecture for a particular class of Davis complexes,
Okay.
arising from flag triangulations of spheres with dimension at least 5.
So they're showing that for these specific triangulations,
Right.
the L2 homology behaves exactly as the Singer conjecture predicts.
Precisely. They achieved this by cleverly utilizing their earlier findings about the vanishing of FL2 homology in certain dimensions after applying iterated edge subdivisions.
It's amazing how they've built this intricate framework
Yeah.
and are now applying it to concrete examples, confirming the validity of the Singer conjecture in these specific cases.
I agree. It's quite satisfying to see their abstract theory come to life in these concrete examples.
Now, things take an interesting turn as they explore the implications of their work for torsion growth in right-angled Coxeter groups. Specifically, they use their results to construct counterexamples to the strong version of the torsion concentration conjecture.
This is where things get really exciting.
Okay.
The torsion concentration conjecture, in its strong form, predicts that the torsion growth for certain groups should be concentrated in the middle dimension.
Okay.
But the authors demonstrate that this isn't always the case.
So they're shaking the foundations of this conjecture
Right.
by providing concrete examples where torsion growth occurs in dimensions other than the middle one.
Precisely, proposition 5.4 lays the groundwork,
Okay.
demonstrating the existence of a specific flag triangulation of a six-sphere whose right-angled Coxeter group exhibits torsion growth in dimension 2.
A six-sphere. We're talking about higher dimensional spaces here.
We are
It's mind-boggling to think about these structures and how their properties challenge our intuitions.
I agree, and they don't stop at dimension 6.
Okay.
They go on to construct similar counterexamples for spheres of dimensions 13 and 20.
Okay, so they've found a pattern here.
Yes.
A way to construct these counterexamples for spheres of increasingly higher dimensions.
And these counterexamples have profound implications for our understanding of torsion growth in right-angled Coxeter groups,
Okay.
demonstrating that the behavior of torsion is more intricate and nuanced than previously thought.
It's like they've opened a new window into the world of these groups, revealing unexpected complexities and challenging established beliefs.
I couldn't have said it better now. Moving beyond torsion growth, the authors present a final application of their work in proposition 6.2.
Okay.
Here they delve into the realm of minimally branching complexes.
Right. Minimally branching complexes, those are the ones with restricted branching patterns, right?
Yes.
I'm curious to see what they uncover in this specific setting.
Proposition 6.2 states that if a minimally branching complex has simply connected links,
Okay.
and its Davis complex is F acyclic in the top 2 dimensions,
Hmm.
then the complex itself must be a specific type of join.
So they're establishing a kind of rigidity for these minimally branching complexes,
Yeah.
showing that their structure is highly constrained under certain conditions.
Exactly. And this rigidity is a direct consequence of their earlier findings about the vanishing of FL2 homology under certain edge removals. It's remarkable how they've woven together these seemingly disparate concepts to arrive at this profound result.
This paper has been an absolute whirlwind of mathematical insights.
Because
We've explored edge subdivisions, barycentric subdivisions, relative barycentric subdivisions, the Singer conjecture, torsion growth, and minimally branching complexes. It's incredible how they've managed to connect these diverse concepts into a coherent and elegant theory.
I completely agree. This paper is a testament to the power of abstract reasoning and the beauty of mathematical exploration. It's a reminder that even in the realm of highly abstract concepts, there's always more to discover, and that new insights can emerge from the most unexpected places.
This has been an incredible deep dive,
It has.
full of surprises and profound insights. Thank you for guiding us through this complex and fascinating world of mathematics.
It's been my pleasure. I'm always thrilled to share the joy of mathematical discovery, and who knows what new adventures await us in the future. There's always another paper, another theorem, another layer of understanding to uncover.
Well, until our next deep dive, let's savor the beauty and complexity of the mathematical landscape we've explored today. All right, let's get ready for a deep dive today. Some intense math coming your way. We're looking at edge subdivisions and the L2 homology of right-angled Coxeter groups, a paper by Grigori Avramidi, Boris Okun, and Kevin Schreve.
Oh, this one's a fun one. It really digs into how these small tweaks to a structure can have these huge impacts on its properties in higher dimensions. We're going deep into the world of right-angled Coxeter groups and their Davis complexes, and this whole concept of L2 homology.
Okay, I'm hooked already, but let's back up for a second. What even is a right-angled Coxeter group?
Okay, so picture a world made entirely of mirrors, but they're not reflecting, like, images. They're reflecting these mathematical structures. And that's kind of the heart of a right-angled Coxeter group. They're all about reflections, but with one big rule. The angle between any two of these reflecting mirrors has got to be 90 degrees.
So it's like a whole system of mirrors, but they're all set up perfectly at right angles to each other.
Exactly. And we can represent these groups visually using diagrams called flag complexes. Like each little dot in the diagram, each vertex stands for a reflection. And if you've got a line, an edge between two vertices, it means those reflections commute. The order you do them in doesn't matter.
Ah, okay, so these flag complexes give us a visual guide to how the group is structured.
That's it. And to take it even further, we can link these groups with these geometric spaces called Davis complexes. Think of them like 3D models built from the instructions in the flag complex.
So we've got these groups represented by diagrams, and then those lead to geometric spaces. So where does this L2 homology fit into all of this?
Well, that's where we start digging deeper into the structure of those Davis complexes. Homology, at its simplest, is like counting the number of holes in a space. You know, a sphere, no holes, donut, one hole, a pretzel, a bunch of holes. L2 homology takes this idea way further. It's like, what if we could measure holes in, like, infinite dimensions?
Infinite dimensions. Now we're getting really abstract.
Yeah, it's pretty mind-bending. But that's where it gets powerful. L2 homology uses these things called coefficients, and they come from a specific type of algebraic structure, a skew field. And that lets us work in these higher dimensions and get a much more detailed understanding of the Davis complex.
So we're using a superpowered microscope to examine the structure of these spaces.
Exactly. And what's really cool is these authors focus on something that seems really simple: edge subdivision. They're looking at how this one little change in the flag complex ripples through the whole Davis complex and changes its L2 homology.
Edge subdivision. It seems almost too simple to have that much impact.
It's deceptive, it's simple, but the effects are huge. Imagine you're taking one of those edges in the flag complex and just like chopping it in half, adding a new vertex in the middle. It changes the whole structure of the Davis complex, and it's L2 homology.
A domino effect.
Yeah.
A tiny change, and then boom, a cascade of consequences.
Exactly. And the authors really get into the specific conditions where this edge subdivision preserves certain properties of L2 homology. And that leads them to some incredible results connected to a really famous unsolved problem, Singer's conjecture.
Okay, now we're talking. Singer's conjecture. A big deal in topology. What's it all about, and how does this research help us understand it?
So Singer's conjecture is about the L2 homology of manifolds. They're these smooth, continuous spaces. And the conjecture predicts that for certain types of manifolds, the L2 homology kind of disappears outside the middle dimension, like all the holes are concentrated in just one dimension.
So it's about trying to find some order in the potential chaos of infinite dimensions.
Right. And the fascinating thing is these authors use their findings about edge subdivisions to tackle Singer's conjecture for a family of manifolds connected to these right-angled Coxeter groups. And they actually prove the conjecture for a couple of specific cases, especially those involving barycentric subdivisions.
Barycentric subdivisions. Can you refresh my memory on those?
Imagine a triangle. Now, add a new point in the center, splitting it into smaller triangles, and then you do the same thing for each of those smaller triangles, and so on. That's barycentric subdivision, a way of dividing a complex into smaller pieces.
Okay, so it's like chopping up a space in a very organized way.
Exactly. And what the authors show is that this barycentric subdivision process, it can actually be achieved by doing a series of carefully chosen edge subdivisions.
I see. So they're connecting these two ways of changing a space edge subdivisions and barycentric subdivisions.
Right, and that connection is key because it lets them use what they know about edge subdivisions to analyze the L2 homology of these manifolds after we do a barycentric subdivision. And amazingly, they prove Singer's conjecture for those specific cases.
That's impressive. So their work actually supports Singer's conjecture for these particular manifolds.
It does, but there's a twist. Remember I mentioned a curveball? That's where torsion growth comes in.
Okay, I have a feeling this is where things get a little weird.
Yeah, you could say that. Torsion growth basically measures how complex certain structures within a group get as you look at larger and larger chunks of that group.
So it's like as we expand our view, we're seeing how much more tangled or knotted the group becomes.
That's a good way to think about it. And there was this conjecture, kind of like Singer's conjecture, but for torsion growth, that suggested a similar pattern of concentration in certain dimensions. But guess what? The authors find examples where this torsion growth version doesn't hold up.
Wait, so even though Singer's conjecture seems to work for these manifolds, this torsion growth version breaks down. What does that even mean?
It means that the holes measured by L2 homology might be neatly arranged in certain dimensions. But when we zoom out and look at the bigger picture, the way those holes grow and interact can be way more complex than we thought.
So the structure might look organized at one level, but when we zoom in or out, things can get messy.
Exactly. And that throws a real wrench into what we thought we knew about the connection between L2 homology and torsion growth. It opens up a whole new set of questions.
So their findings not only support Singer's conjecture, but they also reveal some of its limitations. This paper is a real game changer in how we understand these mathematical objects.
It really is. Now, ready to get into the nitty-gritty? Let's dive into the actual math, starting with some key definitions and lemmas.
Let's do it. I'm ready to see the machinery behind these results. Where do we start?
Let's start with group rings and how they connect groups and fields. It's all laid out on page 2.
Group rings. Bring it on. Hashtag TPS, the Deep Dive episode, 2024-11-13, part 2 of 3.
Okay, so think of a group ring as this way to mix the structure of a group with the arithmetic of a field. Like we're taking two different mathematical recipes, combining them to get something totally new.
I'm following so far. How does that actually work?
So let's say we've got a group, call it G, and a field, we'll call it F. The group ring, we write it as FG. It's basically all these formal linear combinations of stuff from G using coefficients from F.
Formal linear combinations. That's a bit abstract for me. Got an example?
Of course. Let's take our group G to be the integers under addition. And our field F, let's make it the real numbers. So an element in this group ring FG could look like 2 - 1 + 3 + 5, 2.
So we're taking these integers from the group and multiplying them by real numbers from the field.
You got it. And we can add and multiply these things using the rules we get from both the group and the field.
It's like algebra, but with a twist.
Yeah.
We're adding in the group structure.
Yeah, exactly. And these group rings are super useful for studying groups and what they do. In this paper, the authors use them to get into this idea of equivariant homology, which is a way to measure the homology of a space, but also taking into account how a group acts on that space.
Equivariant homology. Sounds like we're adding even more layers here.
We are, but it's important if we want to really understand how groups and spaces work together. Think about a group doing something to a space, like rotating a sphere or reflecting it. Equivariant homology helps us figure out how that group action changes the homology of the space.
So we're watching how the holes in the space change as a group moves it around.
Yeah, great visual. And in the paper, they use a specific type of this equivariant homology that uses coefficients from skew fields, which are fields where multiplication doesn't have to be commutative.
Hold on. Non-commutative multiplication. Isn't that a recipe for disaster?
It can be a bit tricky, but it turns out that these skew fields are actually great for studying L2 homology, which is a big deal for this paper's results.
Okay, so ski fields let us work with L2 homology. But why are they so important here?
Well, remember we talked about how the specific skew field you use can affect those L2 Betty numbers you calculate. This is where a certain kind of skew field, a Linnell skew field, becomes really important. They have this property called injectivity, which really helps with this issue.
Injectivity, what does that mean in this context?
Basically, it means that when you narrow down a Linnell skew field to a subgroup of the group you're looking at, you don't lose any information, like a perfect zoom lens. You can focus on a specific part of the group without distorting anything.
I see. So Linnell skew fields give us a clear and accurate way to study L2 homology.
Precisely. And because of that injectivity, they have a certain universality. If you calculate L2 Betty numbers using a Linnell skew field, it's like getting the maximum possible value. You've found the most efficient way to measure the complexity of the group.
That's powerful. Linnell skew fields are like the gold standard for L2 homology.
You could say that. They provide a really solid foundation for everything the authors are doing. Now, on page 3, the paper starts talking about this idea of virtually existing Linnell skew fields.
Virtually existing, what does that mean?
It means sometimes a Linnell skew field might not actually exist for the group itself, but it might exist for a finite index subgroup of that group. It's like we're expanding our search to include related groups.
So even if the group itself isn't ideal, there might be a smaller group inside it, that is.
Yeah, good way to think about it. And even if we can only find a Linnell skew field for a finite index subgroup, we can still work with L2 Betty numbers for the original group. So we can apply the author's results to even more types of groups.
So these virtually existing Linnell skew fields give us more flexibility with these tools.
Exactly. And then the paper introduces FL2 Betty numbers, which are like a broader version of the usual L2 Betty numbers. We're using coefficients from a field F instead of just real or complex numbers.
So we're measuring the size of these homology groups with a different ruler.
Good analogy. And the authors prove this really important lemma 2.4. It shows that if a Linnell skew field virtually exists, then the FL2 Betty numbers of a special kind of induced space are equal to the FL2 Betty numbers of the original space.
Induced spaces. Remind me what those are again.
Think of them as spaces you build by expanding a smaller space based on a group's structure, like taking a blueprint and using it to make a bigger building.
Okay, so lemma 2.4 tells us that expanding the space this way doesn't change the fundamental size of the homology, at least as measured by those FL2 Betty numbers.
Exactly. And that fact, that it doesn't change, is a key part of their later analysis of edge subdivisions and how they impact L2 homology. Then the paper shifts gears a bit. We're back to those right-angled Coxeter groups and their Davis complexes.
Back to the world of mirrors. I'm excited to see how these abstract tools get applied to these geometric objects.
Well, one of the cool things about right-angled Coxeter groups is they always have this normal subgroup called the commutator subgroup. We'll call it CL for a group WL.
The commutator subgroup, that's the part that captures the non-commutative structure, right?
Exactly. And it has some nice properties. It's torsion-free, meaning it doesn't have any elements that loop back on themselves after a certain number of operations. It's also residually torsion-free nilpotent, which basically means we can approximate it with a series of simpler, nicer groups.
So it's like taking a complex object and breaking it down into smaller, easier to understand pieces.
Right. And these properties let us use all those tools from skew field theory and L2 homology to study these groups. On page 4, they introduce mirrored spaces, these geometric things with a bunch of mirrors.
We're actually talking about mirrors now.
Not like the ones on your wall, they're more like subspaces of the bigger space. And they're really important for building the Davis complex, which we denote.
The Davis complex, that's the geometric version of the right-angled Coxeter group, right?
You got it. We build it by taking the group and kind of gluing it together with a mirrored space that's made specifically for that group. The result, the Davis complex, it's called a CT0 cubical complex, meaning it's made from cubes and it has nonpositive curvature.
So a really structured and well-behaved geometric object.
Definitely. And one of the key things about it is the Davis complex is contractible.
Contractible, what's that?
Imagine you have a balloon and you let the air out slowly until it's just a single point. That's kind of what contractible means. The Davis complex can be shrunk down to a point without ripping or breaking it.
So it's a very flexible space, topologically speaking.
Exactly. And that makes it much easier to analyze the homology of these spaces. Now, the paper then gets into flag subcomplexes.
Flag subcomplexes. Are those like smaller versions of the Davis complex?
You got it. A flag subcomplex is basically a smaller Davis complex living inside the bigger one that comes from the whole group. It's like you're taking a subset of the rules that define the group.
Like taking a blueprint and highlighting a specific section to build something smaller.
Perfect analogy. And these flag subcomplexes are key for understanding what happens when we do those edge subdivisions. To analyze the impact of edge subdivisions on homology, the authors use this tool called the Mayer-Vietoris sequence.
The Mayer-Vietoris sequence, we've talked about that before, right? It's like a divide and conquer approach to homology.
Exactly. We break the space down into smaller pieces to understand the homology.
So how do they apply that to edge subdivisions and Davis complexes?
Picture a Davis complex. Now, do an edge subdivision on the flag complex. Boom, new Davis complex. The Mayer-Vietoris sequence lets you relate the homology of this new subdivided complex to the homology of the original one and the homology of the parts that changed because of the subdivision.
So we're comparing the homology before and after the changes.
Exactly. And what the authors show is that sometimes edge subdivisions actually keep certain homological properties the same. Even though the geometry changes, some aspects of the homology stay stable.
So it's not like these subdivisions completely scramble the homology. They make changes, but there's a pattern to it.
Precisely. And these stability results are really important for understanding how edge subdivisions affect the L2 homology of these groups. We can control the changes and see what happens to the structure.
This is fascinating. Can we dig into the specifics of what they find about the FL2 homology of right-angled Coxeter groups based on these subdivisions?
Absolutely. One of their key results is theorem 3.3 on page 6. It's all about what happens when you subdivide an edge where the link is FL2 acyclic.
FL2 acyclic. Quick reminder on that one.
Sure. It means all the FL2 Betty numbers of the link are 0. Think of the link like the neighborhood of the edge we're subdividing. So an FL2 acyclic link, it's like saying that neighborhood is homological, simple.
Okay, so we're subdividing an edge in a simple part of the flag complex.
Right. Theorem 3.3 says that if we do that subdivision, the FL2 Betty numbers of the new complex are like bounded above by the FL2 Betty numbers of the original one. Basically, subdividing an edge in a simple spot doesn't make the overall homology more complex.
It's like saying that this little change doesn't make the whole thing messier.
Exactly. And there's a really important consequence to this theorem. If the original complex had vanishing FL2 homology in a certain dimension, the subdivided complex will too.
So simplicity is preserved.
Right. And that's a big deal for the author's analysis of Singer's conjecture and torsion growth. They can control what those subdivisions do and see how they affect these important properties.
Okay, can we take a look at the proof of Theorem 3.3? I want to see how they actually show this preservation of vanishing FL2 homology.
Oh, it's a great proof, a perfect example of how they use all these different tools to get a powerful result. The basic idea is to split the original flag complex into 3 pieces. You've got the star of the edge that's being subdivided, the suspension of the link of that edge, and then everything else, which they call R.
So they're breaking down the complex into the edge itself, its immediate surroundings, and then everything else.
Exactly. And that lets them use the Mayer-Vietoris sequence to connect the homology of these pieces to the homology of the whole complex.
The act to divide and conquer.
Exactly. And the key insight here is that because the link is FL2 acyclic, the homology of the star of the edge and the suspension of the link also vanish in that dimension where we're trying to prove vanishing. So That simplicity from the link spreads to these bigger pieces of the complex.
That initial simplicity assumption is really carrying a lot of weight.
It is. And because those pieces have vanishing homology, they basically disappear from the Merivia-Torres sequence. What we're left with is a connection between the homology of R, the part we care about, and the homology of the original complex.
So they've isolated the part of the homology affected by the subdivision.
Exactly. Now, they use lemma 2.6, which is a cool result from skew field theory. It links the FL2 Betti numbers of a space to the FL2 Betti numbers of a particular cover of that space.
So they're comparing the size of the homology at different levels of zoom.
You got it. And using lemma 2.6, plus the properties of that Linnell skew field, they show that the FL2 homology of R also vanishes in that dimension, proving the theorem.
Very elegant proof. They really weave these different tools together.
It's beautiful. Now, they use this theorem to explore a bunch of other applications of edge subdivisions, like their connection to minimally branching complexes, barycentric subdivisions, and of course, Singer's conjecture and torsion growth.
Okay, I'm excited to hear more about those. Let's start with minimally branching complexes. What are those, and how do edge subdivisions play a role?
Minimally branching complexes are, like the name suggests, very sparse structures. Specifically, in one of these complexes, each n2-dimensional simplex is in at most 3 n1-dimensional simplices. Think of a network where the connections between different dimensions are really limited.
A loosely connected structure.
Right. And the authors use their edge subdivision results to prove this really interesting theorem about the L2 homology of these minimally branching complexes.
Well, tell me more.
They show that the L2 homology of a minimally branching complex of dimension n, it vanishes in dimension n, unless the complex is a very specific structure, an n-fold join of 3 points.
An n-fold join of 3 points. What's that look like?
It's this really symmetrical and connected structure. Start with 3 points, connect them with edges to make a triangle. Now take 3 of those triangles and connect them to make a tetrahedron, a pyramid with a triangular base. Keep repeating that, connecting copies of the previous structure until you get to the nth dimension.
So it's like this network of triangles and tetrahedra.
Exactly.
And
what their result says is that for these minimally branching complexes, this n-fold join of 3 points is the only time the L2 homology doesn't vanish in dimension n.
Interesting. So in these loosely connected structures, the L2 homology is almost always 0 in that dimension, unless we have this really specific symmetrical structure. You'd think a loose structure would have more holes, not fewer.
You'd think so. But it shows this really subtle connection between how connected a complex is and its L2 homology. And the key to proving this, it all comes down to edge subdivisions.
Okay, walk me through how they use edge subdivisions to prove this result about minimally branching complexes.
Okay, so the proof uses induction and edge subdivisions. They start by assuming the result is true for all minimally branching complexes in dimension, n1.
Classic induction, assume it's true for a smaller case, then prove it for the bigger one.
Exactly. Now, we have this minimally branching complex L of dimension n. They look at a few cases. First, if L isn't connected, if it's made of separate pieces, then we can just use the induction hypothesis on each piece easy.
So we can basically ignore the case where L is not connected.
Right. The next case is where the link of some vertex in L isn't an n1-fold join of 3 points.
So we're assuming there's at least one point in the complex where things aren't perfectly symmetrical.
Right. And in this case, the induction hypothesis says the L2 homology of this link vanishes in dimension n1.
So that imperfection in the link leads to vanishing L2 homology.
Exactly. And this is where theorem 3.3 comes in. Because the link of this vertex has vanishing L2 homology in dimension, n1, we can use the theorem to just remove the vertex without changing the L2 homology in dimension n.
Wait, we can just take out a vertex and the L2 homology stays the same.
Yep. Theorem 3.3 guarantees that removing this vertex won't make any new holes in dimension n.
Incredible. It's like that vertex was invisible to the L2 homology in that dimension.
Exactly. And if you keep doing this, taking out vertices with imperfect links, eventually you're left with a singular complex where every vertex has a link that is an n1-fold join of 3 points.
So they've simplified the complex by getting rid of all the imperfections.
Exactly. The last step is to analyze this simplified complex where every vertex has a perfectly symmetrical link.
What happens then?
They show that in this case, the complex itself has to be an n-fold join of 3 points.
So that perfect symmetry in the links forces the whole complex to be symmetrical.
Yes. It's a really cool result that comes from carefully looking at edge subdivisions and how they work with minimally branching complexes.
This is all so insightful. These simple operations, like edge subdivisions, can have such huge consequences for how these complexes are structured.
It's really amazing. It shows how connected all these mathematical ideas are.
We've covered a lot today, from group rings to edge subdivisions and minimally branching complexes, but I'm still excited to hear about Singer's conjecture and the torsion growth phenomenon. Ready to dive into that?
Let's do it. It's time to tackle those mysteries. Hashtag TTS, the Deep Dive, episode 2024-1113, part 3 of 3.
All right, so we've gone through these minimally branching complexes and how those edge subdivisions help us understand their L2 homology. Now for the main attraction, Singer's conjecture and that whole torsion growth thing. What's the starting point?
Well, remember Singer's conjecture, it basically says that for a closed aspherical manifold, the L2 Betty numbers disappear outside of the middle dimension. All the holes, at least the ones measured by L2 homology, they're all concentrated in just one dimension.
Right, like the manifold is balanced in terms of those higher dimensional holes.
Exactly. And one of the big things this paper does is they actually prove Singer's conjecture for a specific family of manifolds that are linked to right-angled Coxeter groups.
So they're using everything we've talked about, edge subdivisions, barycentric subdivisions, Linnell skew fields, to tackle this conjecture.
You got it. And they're combining all these techniques in a really clever way to study this particular family of manifolds.
Okay, tell me about these manifolds. How are they constructed? What makes them special?
The manifolds they look at are built from right-angled Coxeter groups, where the nerves are barycentric subdivisions of triangulations of spheres. So you take a sphere, divide it into triangles, then do a barycentric subdivision on that triangulation, and then you use that subdivided structure as the instructions for making a right-angled Coxeter group.
So it's like taking a simple shape, a sphere, and then adding all these layers of complexity with the triangulation and subdivision, and that leads to a manifold.
Yeah, it's a great way to picture it. And the Davis complexes that come from these right-angled Coxeter groups, they turn out to be manifolds with some really interesting properties.
All right, so we've got these special manifolds. What do they do with them?
They use those results we talked about earlier, the stuff about edge subdivisions, barycentric subdivisions, Linnell skew fields, to analyze the L2 homology of these manifolds. And what they find is amazing. The L2 Betty numbers of these manifolds, they really do vanish outside the middle dimension, just like Singer's conjecture predicts.
That's huge. So they've found concrete evidence supporting Singer's conjecture in these cases.
They have. And it's a perfect example of how all these abstract tools, like edge subdivisions and skew fields, can help us solve real problems in topology and geometry.
Okay, so they've made progress with Singer's conjecture, but what about that curveball, that torsion growth thing? Remind me what that was all about.
Right, torsion growth. It's all about measuring how the size of certain subgroups in the homology groups of a space grows as we look at bigger and bigger finite covers of that space. It's like how much more twisted does the space's structure get as we zoom out?
Like measuring how tangled a rope gets as we add more strands to it.
Exactly. And there was this conjecture, kind of like Singer's conjecture for torsion growth, that said this growth should also be concentrated in certain dimensions, just like the L2 Betty numbers.
So it made sense to think torsion growth would follow a similar pattern to the L2 homology.
It did. But here's where it gets interesting. The authors find examples where this torsion growth conjecture doesn't work.
Hold on. So Singer's conjecture seems to hold up, but this torsion growth version doesn't. What's going on there?
It means those holes, measured by L2 homology, they might be organized in those specific dimensions. But when we zoom out and look at the whole picture, the way those holes grow can be a lot more complicated than we thought.
So the structure looks nice at one level, but zoom out and things get wild.
Exactly. And that really changes how we think about the connection between L2 homology and torsion growth. Opens up a whole new set of questions.
Give me some details about these examples where the conjecture doesn't work. What do they look like? How do they break the expected pattern?
They're pretty complex, but the key is those relative barycentric subdivisions.
Right, where we subdivide some parts but leave others alone.
Yeah.
Like choosing which parts of the structure to refine.
Exactly. And the authors use these subdivisions in a really clever way to build flag complexes with specific properties, and then they use those flag complexes to build manifolds that break that torsion growth conjecture.
They're designing these complexes specifically to create these counterexamples. Can we go through one specific example?
Sure. One example uses a three-dimensional flag complex. They call it A-well. And this complex has an interesting property. Its L2 Betty numbers are 0, but its Fe Betty numbers, for a certain prime number P, they're not 0.
SP Betty numbers. Those are the ones where we use coefficients from the field FP, right? The one with P elements.
That's the one. And this difference, the L2 Betty numbers being 0, but the FP Betty numbers not being 0, that's really important for making this counterexample. It shows that the L2 homology isn't giving us the whole story about this complex.
Okay, so we have this complex OL with this unusual property. What's next?
They take AOL and embed it as a full subcomplex into a triangulation of a sixth sphere.
So they're putting this three-dimensional complex inside a six-dimensional sphere.
Exactly. And then they do a relative barycentric subdivision of the sixth sphere, but they leave AOL untouched.
So they carefully subdivide the sphere around this special complex OL.
Right. And what you end up with, they call it T. It's a flag triangulation of the sixth sphere. But it has some interesting things going on because of OL.
What kind of things?
Well, since OL had those non-vanishing FEP Betti numbers, T ends up with non-vanishing FP Betti numbers in some dimensions too.
So that non-vanishing property gets passed on to T, even though it's a triangulation of a sphere.
Exactly. And this is where it gets really cool. The manifold that comes from T, which is a 7-dimensional manifold, it breaks that expected torsion growth behavior.
Wow. So by carefully putting AOL into a sphere and doing this relative barycentric subdivision, they create a manifold that violates the torsion growth conjecture.
They do. And this counterexample really shows the subtle difference between Singer's conjecture, which is all about L2 Betty numbers, and that torsion concentration conjecture, which deals with torsion growth. They're related, but not always the same.
This is mind-blowing. What does this mean for future research? What are the big questions now?
Well, it changes how we think about torsion growth. We know now that torsion growth and L2 homology are connected, but not as closely as we thought.
It's like two rows we thought ran side by side, but actually they split at some point.
Perfect analogy. And that split leads to new questions. When does the torsion concentration conjecture actually hold true? Can we come up with a new version of it that explains what we see in these counterexamples? How is torsion growth connected to other geometric and topological ideas? These are all questions that'll drive future research.
This paper is a real treasure trove of mathematical mysteries. It's amazing how something as simple as an edge subdivision can lead to such incredible discoveries and make us rethink what we know about these concepts.
It really shows the power of curiosity and the beauty of math. It's a reminder that math is always changing, always growing as we explore it.
Absolutely. Any advice for our listeners who want to learn more?
Read the paper. It's tough, but worth it. There are also some great online resources that introduce right-angled Coxeter groups, L2 homology, and torsion growth divergently. And stay tuned for more research in this area. Who knows what else we'll find?
Awesome advice. Thank you so much for taking us on this deep dive into edge subdivisions and everything they affect. It's been eye-opening.
My pleasure. I hope our listeners are inspired to keep exploring the world of math. It's full of amazing discoveries.